Okay. Good afternoon. How are we today? Right. Last week we talked about recycle, and this is one of very important concept of the recycle. So I want you to work with me to realize how important is the recycle stream. Okay. Settle down, please. Settle down. Settle down. Don't talk. Okay. Right. Are you listen to me? Hello. Settle down. Okay. All right. Okay. So I want you to work with me about this uh, this example, which is very important for the recycle, because we are talking about single pass conversion and overall conversion. So overall single pass conversion, overall conversion is that if you have a very not very good reactor, so you can use a separator to recycle the unreacted products and recycle the unreacted reactant. I'm sorry, unreacted reactants. So you can make the overall efficiency very high. So this is one of the example telling you that once you only if you only introduce 100 moles per hour of the C3H8 and you recycle a lot of the C3H8 back to this reactor through this recycle stream, which is very important because as you can see, you have 995 C3H8 into this reactor and then come out with 900 C3H8. So as you can realize that the conversion rate is not so good because assume you introduce 1000 moles per hour of these A materials and come out reactor with 900 A reactants. And that means the conversion rate is very low. So the single pass conversion for this is only 10% for this reactor. However, you have a very good separator. And then, the mixture of this, the products from this reactor is 900 C3H8 and then about 100 C3H6 and then 905 H2. So as you know that this is a very bad mixture. And then luckily, fortunately, these products went into this separator and then come out with a very good product streams, which has about 95 C3H6. So as you can see, the single pass conversion is only 10% because this one minus this one divided by this one is about 10%. And then as you know that about 99.5% recycle back to this, the reactant recycle back to this reactor. So which is a lot, And then for the overall conversion, which is 100, and this one is 95. So as you know that 100 minus 5 here, I'm sorry, minus 5 here. So overall conversion is about 95%. So it's good. Okay, so this is one of purpose for the recycle stream. Okay, so in order to have a high overall conversion, you have two methods. The first method is you have a very good reactor, so you don't need to have this separator. The method one. Method two is that if you don't have a good reactor and you need to have a separator in order to have a good overall conversion rate. Okay, so this is very important. We talked last week. And today, we want to introduce you another new topic, which is purging. We call purging stream. So let me make an example for you. Let's make the same example as the example I gave you last week. This is a reactor. This is a separator. So you have a fresh feed here, and you have a recycle stream. And this is a kind of chemical reaction, and then you have a purging stream here. And then you might wonder why, when the things come out from the separator, this is product stream, this is recycle stream, and we want to have a one come out to the split out from the recycle stream, which is purging stream. why we need to do that. Okay, this is the reason. So assume you have a chemical reaction which is react with oxygen. So as you remember, once you have something react with the oxygen, normally you don't put pure oxygen in. Why? Because it costs money. No, so normally you put air in, because air has 91% more of the oxygen. It's free, right? So you just pump the air into this reactor. Then you might ask, you might raise a question: why? What happened to the nitrogen? What happened to the nitrogen? Okay, so nitrogen is a kind of inert gas, so it's a kind of non-reactant. But according to this, if you don't have purging stream here, nitrogen will come out with the products, or nitrogen never come out with product, because if the product doesn't need nitrogen, so the nitrogen will do the cycle, a kind of closed loop in this system. And what happened in the end? That you will keep on feed nitrogen into this system, and nitrogen never come out. So what happened? Reactor explode. You have a problem with the danger. You have a problem with human being, right? So this is very serious. So that's why we need to release some of the nitrogen away from this system. This is the reason why we need purging stream. Okay, so this is a release the undesired products or substance away from this system. And then if there is a non-reactive material in the process, purge is necessary. Otherwise, the material will accumulate in the process until shutdown. Shutdown means what? This reactor explode or separator explode. Too much pressure, too much substance. Okay, I will give you an example very soon. So I just want you to know this is the purpose of the purging. So if you want to do mass balance using this system, of course here, right? If you have a stream from the separator and this kind of splitting point. Split point means what? I hope you remember. The ratio will be the ratio of this substance will be the same, but different amount, of course. Or sometimes it can be a same amount. It depends. Okay, and this is split point. The key is that the fraction of the substance in this stream will be the same fraction of the substance in this stream. Okay. So this is one point, split point, and this is what? This is mixing point. As you remember, as you remember last week, we introduced mixing point to you here. Mixing point to you. Okay. Right. So example figures 4.7-2 telling you that this is one of reaction. That means we want to make these products C2H4O by C2H4 plus oxygen. So as you know that we don't really want to introduce oxygen into this reactor. We want to introduce air in this reactor. Okay, so you have some portions, or sometimes we don't want to have this reaction so serious, so well. So we introduce some kind of inert gas. So we dilute the concentration of oxygen. In that case, we don't have a very fast reaction. Okay, this is the purpose of inert gas. In this case, it's nitrogen. Okay, so this is the one of the example telling you that we need to introduce nitrogen into these reactors, and nitrogen doesn't do anything here. Well, I should say doesn't do anything with the reaction, but it does has a purpose of the dilute the concentration of the oxygen, or speed down of the chemical reaction, for example. Okay, so the reactor will go through, the nitrogen will go through the reactor without doing anything, and then it will go through a separator. And then if the product doesn't need nitrogen, for example, this separator is kind of gas liquid separator. So all the gas will go through this way, and then all the liquid will go through this way. And in that case, nitrogen will go through this way, right? However, if you don't have purging stream, the nitrogen will be a closed loop in this cycle, right? And you will have trouble. That's why you need purging stream, okay? So the input is C2H4 and O2 and N2. And then, the output stream will be there are two output streams. One is product stream, which is C2H4O. And this is subscript here is L. L stands for liquid, right? The subscript here, G is represent gas. So this is kind of condenser. All the gases products go into this separator, and some of the product condensed, become liquid from gas to liquid. This condenser, which is C2H4O, and others like C2H4 and O2N2 doesn't condense, so you will go through this way. Okay, and you have a purging stream. You release some of the product away. Okay, so purging stream is that C2H4, O2, and N2. Okay, here I want to address something here to you is that this is in gas phase, because in the reactor you produce C2H4O, which is 环氧乙烷, right? And then this is in the gas phase. After it come out from the reactor, and then you have a condenser, it becomes liquid. So this liquid all comes through this way, and you will have a very pure products of the C2H4O, which is very good. Okay, and you have nitrogen here. Right. So this is one of the example. Okay, so now I want to let's go to the page 133, example 4.7-3, and this is an important example, and it is very likely. This question is very likely to be in your final exam paper. So I want you to work with me so you can have a good score in your final exam. Okay, so let's go through this first. And so you have, I hope you have the text with me. You have text with me, right? Print out, or you can a PDF file. Okay. So let's go. So methanol is used as a raw materials in the manufacturing of the formaldehyde, acetate acid, and NTBE, and a number of the other important chemicals. So this is one of important chemical reaction. Okay, it also has many other use, including a solvent, blah 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 blah. Okay, so this is the chemical reaction here. Okay, so the second paragraph, the fresh feed to a methanol synthesis process contain hydrogen, carbon dioxide, and 0.4 more percent inert gas, inners. Okay, so you understand, if you want to have a chemical reactor, this is you have hydrogen, carbon dioxide, and 0.4 more percent inert gas. So this chemical reaction is on the slide here. Okay, so the reactor influence passes a condenser that remove essentially all of the methanol and water, foam, and none of the reactants or inners. So this is reactor. After reactor, there is a condenser, right? Condenser. And condenser allow things to condense. Okay, so methanol, water, foam, and none of the reactants or inners. Okay, the later substance are recycled to the reactor. To avoid build up the inner gas in the stream, a purging stream is withdrawn from the recycle. So this is important concept to telling you that the importance of the purging stream, right? Right. So okay. So let's start to work from here in the third paragraph. The feed to the reactor. The feed to the reactor. Okay. There's a parenthesis blank. Not the fresh feed to the process. It's not a fresh feed to the process, but it's the stream to the reactor only. Contain 28% more carbon dioxide, 70% hydrogen, and 2% inert gas. Okay, so please work with me on the slide here. So we have fresh feed, and then what? And then we have hydrogen, right? Hydrogen, carbon dioxide, and some inert gas, which is 0.004, right? 0.004. Okay, so this is what we know. And then this one going to the reactor. Okay, this one going to the reactor. And then the reactor, after the reactor, we have a separator, which is a condenser. So condenser condense something away out in the liquid form. And some of them, so which is, we have C3HO and then H2. So these two will be condensed because water and the methanol is easy to be condensed. Okay, and then you recycle the products, reactant back, non-reactant back here. They are what? So this is called recycle stream. Okay, and in order not to build up the reactants in this cycle, we have a purging stream, right? So this is mixing point, and we will have C2, H2, and inert gas, the same as this CO2, H2, and inert gas. Okay, and then what? And then we have a purging stream. Okay. So I think in your final exam, I don't think I will give you this flow chart. So you need to draw the flow chart by yourself, I think, according to the description of the question. Okay. So basically, the flow chart will be exactly the same. It's just the different but I will give you the different numbers. Right. So this is split point. So you know that split point and the mixing point here. So again, if the come out with the carbon dioxide, hydrogen, and the inert gas, of course, in the recycle stream you will have carbon dioxide, hydrogen, inert gas, and in the purging stream, of course, you will have carbon dioxide, hydrogen, and inert gas, right? Okay. So, and now now it's important. Let's go to the text, the third paragraph. Start with the feed to the reactor. Okay, the feed to the reactor, not the fresh feed to the process. This stream on the slide. This stream is what? This stream is the fresh feed to the process, but this stream is the feed to the reactor. So they tell us that the feed to the reactor contain 28% more carbon dioxide, 70% hydrogen, and 2% more inert gas. So let's write down here. We have 28% carbon dioxide in the slide here, and we have 70% hydrogen, and then we have 2% inert gas. This is what we know, right? Okay, so let's move to the third paragraph, the line 2. Okay, this is specification. The single pass conversion of hydrogen is 60%. So they tell you that in this slide, the reactor, the single pass conversion of hydrogen is 70%. So what's that? So this is one of the specification, right? As long as you know the definition of single pass conversion, and you know that here, if you have, for example, if you have 70 moles and the single pass conversion is 60, so you know that the output of the hydrogen here. Okay, this is one of the specifications here. Right, so that's all the information we have got. So in the third paragraph, line 2, in the end of line 2, calculate the molar flow rates and the molar compositions of the fresh feed, the total feed of the reactors, and the recycle stream and the purging stream for the methanol production rate. Okay, this is one of the important key here. They tell you that the purging stream for the methanol product rate is 150 kilomoles per hour. So what does that mean? They're telling you that this is 155 kilomoles per hour. Okay. So in a slide here, you see that the methanol is 155 kilomoles per hour, and then they ask us to get unknowns from all these parts. Okay, so this is what we have. Right. The important key for this question is that basically first of all we need to choose the basis, but since the basis is here, unfortunately, if you regard the basis here, it will be difficult for you to do a calculation. So first of all, this example telling us that forget about this one. Forget about 155 kilomole per hour. You set a basis first, which is easier. And then once you do all the calculations, you convert these numbers by ratios. Because if you set a basis here, this is what they told us. You can set a basis here, but you don't want to give yourself trouble because this has not enough information. But if you set a basis here, basically we set a basis here. Okay? We set a basis here instead of this place. And then you have all the information here. That will be easier for you to get all the answers. Okay? And then in the end, if you set a basis here, assume you have basis here 100, and you'll get a number here. And once you know the number, for example, if this number is, and in the end, if you got the answer of the methanol is 15.5 kilomole per hour, that means what? That means all the numbers you just need to type 10 times. Okay? So, are you with me so far? This is important. I just want to let you know that forget about 155 first. And you set a basis here. And once you set a basis, you got all the answers of all the streams. And in the end, you found the answers of this CH3OH is, for example, 15.5 kilomole per hour. That means what? That means this is about 10 times of the answer you got. So all the numbers you just times 10. That will be the final answer. Okay. Okay. So, but if you know the answer, you understand this is you need to do this in the very end. Okay. Right. So now let's start to put the unknown in this flow chart. First of all, let's do it here. You have N0, and then you have X, and X sub OC. C stands for carbon, right? O is 0 is the same number because you are from the same stream. So you use the symbol like this. And because you know that this is 0.004, so obviously you understand this. You have a ratio of 1 in these three components. So if it is X06 OC, that will be 1 minus O 0.004 minus X sub OC. So there are two unknowns here. Okay? And then you have all the information in this stream. And now let's put the unknown in this stream. If there's no ratio, and then I will suggest you to put the mole here. You don't want to know about, you don't want to regard the sum of ratios. So you put N1, N2, N3, N4. You might say, well, Professor, why I don't do N5 here? Because this is the reactant, right? This is reactant. And inner gas doesn't do anything in the reactor. So 100 times 2, that will be 100 times 0.0002, that will be 2. So you don't want to put the unknown here. This is one of the specification, but anyway, that will be easier for you to reduce the unknowns. Okay, so you have 4 unknowns here. Right. And the tricky part is in this place. This is the condenser. So you separate gas and liquid completely. Assume completely. So if you have C, so that means all the CH3OH will be in this stream. All the carbon dioxide will be in this stream. So here the unknown will be what? Unknown will be N3, right? N3. Unknown will be N4 because all the water and the methanol will be condensed. So you know that you don't write N5, N6 here. You don't want to give yourself trouble, right? Okay? Right, okay. So that's it. And then you might think, well, Professor, can I write N1, N2, N3, N1, N2 here? Basically, yes. But unfortunately, you want to find the ratios because there's a ratios. So you don't put N1 and N2 here. You just put N5, which is the total amount of the carbon dioxide, hydrogen, and inner gas. Okay, but again, you know the inner gas. You know this one. You know X. You do the fraction, which is X. X 5 sub 5C and X sub 5H. And of course, you know this 1 minus X sub 5C and minus X sub 5H. You might think, wow, Professor, why we need to do this? Why we need to give ourselves trouble? Because as I just told you, purging stream and recycle stream, they have the same fraction, right? You just split the moles away from one to another. So the ratio of this carbon dioxide, hydrogen, inner gas will be the same. So that will be easier for you to assume the unknowns here. So the important key is that splitting point is the same molar fraction, right? So you can write down P stand for purge, right? So this X5C and X5H will be the same as this one. The only difference is MP. You just add one unknown here only. Okay, to reduce the unknowns, that's the way you need to do. Okay, so you do the N sub R here. R stands for recycle. Again, the fraction here will be the same as this one and this one. So you only increase only 2 unknowns, which is N sub P and N sub R. P stands for purging stream. R stands for recycle stream. Okay. Right. Okay. So this is. So we complete all the unknowns in the flow chart. Okay. So now let's start to work from the basis and then DOF and then do the calculation. So in the page 139, as a general rule, a combined feed to the reactors is a convenient stream to use as a basis of the calculation for recycle problems. So remember this key point, okay? So when the stream composition is known, we will therefore temporarily ignore the specific methanol product rate, which is 155, right? Kmols per hour, okay? Balance the flow chart for the assumed basis, which is what? 100 kilomoles per hour. Okay, and then scale. This is important. After that, you do the scaling. Scale the process to the required extent. Right. So let's do it. Second, basis 100 kilomoles, or you can say 100 more as you like. Combined feed. Third, flow chart. Okay, you finish the flow chart, and fourth, you do the DOF. Okay, so how can we do the DLF? First is overall system, overall unit system, right? So overall unit system, if we do the overall unit system here, then we need to conduct with what? We need to conduct with atomic balances. Why? Because the overall unit system involve chemical reaction. So as we know from the last week, we suggest you to use atomic balances, which is easier for you to do the calculation. But before you do this, let's do the DOF. So there are four terms in the DOF for the atomic balances. The first term is what? Unknown, right? The second term, I hope you remember, independent atomic species balance. How many atomic species involved in this reaction? The third one is molecular balances on independent non-reactive species. So if this system involve inner gas, you need to do the molecular species balance, especially for the inner gas. Okay, and then fourth, other equations relating unknown variables. Okay, like remember that, like single pass conversion specification, physical laws, and physical constraints. Okay, so that's it. So let's do it in overall system. So please tell me how many input and how many output in overall system. Anybody want to tell me? I want to give you 0.5 point, please. Yes. Huh? One input to output, right? Okay, thank you. I'm sorry, I'm very happy somebody raised your hand very fast. Okay, so please, this is a little bit more, right? So we have, sorry, I don't want to, okay, so we have one input to output, okay? So I'm sure you know that. How many unknowns here? I'm sorry, you already know the answer, so I don't want to give you points. So if you block here, one input, two outputs, so you need to start to count how many unknowns. 1, 2, right? 3, 4, 5, 6, 7. There are 7 unknowns. There are 7 unknowns. Okay, so second term is independent atomic species balance. Please tell me how many independent atomic species balance. How many? What's the number here? 3, right? 3. Carbon, oxygen, and hydrogen. Yeah, 3. Okay, so anything involved with the chemical molecular balances on independent non-reactive species. Do you have anything? No. You have one, right? You have inner gas. Sorry, you have inner gas. Okay, so you can do the molecular balances. But anyway, you already put the numbers here. Right, okay, so is any other specification? No. So unfortunately, you cannot get the answer of these 7 unknowns. This is one of the okay, so right, so now let's do a single unit system, because we finished overall unit system and it doesn't work. So let's go to the single unit system. So there are 1, 2, 3, 4, right? There are 4 single unit system. And then which one you think you want to go first? Okay, the one has less unknowns and the one has more specification. Okay, so which one? So this one has one input, two input, right? And one output. How many unknowns? 1, 2, 3, 4, 5. Right? Okay. And this one input, one output. How many unknowns? 1, 2, 3, 4. Okay, this one has one input, two output. How many unknowns? 1, 2, 3, 4, 5, 6, 7. And this one input, two output. How many unknowns? 1, 2, 3. Well, this one might be easier. Right? No. 1, 2, 3, 4, 5, right? 5. So, and then where is the specification? This is the specification from between the input and output. So if I were you, I would choose this reactor first because this has less unknown and more specification. And again, we need to do atomic species balance. So again, let's write down here. So you have one input and one output, easier. So how many unknowns here? 1, 2, 3, 4. We have 4 unknowns. And then how many independent atomic species balance? Again, carbon, oxygen, and hydrogen, right? So we have 3. And do we have molecular species balance? 1, right? 1. But no, actually, I use blanket here is because you already use these unknowns because there's no unknown. You don't make red mark here because you already use this specification. Sorry, you already use these balances already. So ignore this one. Okay, and then what's the other equations relating unknown variables? 1, right? Which is single pass conversion. And you need to remember the definition of the single pass conversion. Okay, so 4 minus 1 equal to 0. So that will be 0. So you can achieve this one, this one, this one, and this one, N1 to N4. Again, I don't want to waste your time to do this kind of easy calculation. You do it by yourself. Okay, so because we use the single pass conversion for the mass balance, I'm sorry, I restart. We use the reactor for this mass balance, so we get N1, N2, N3, N4, right? So let's mark it from red to the blue. So we got these 4 numbers. So what's the N? And then which one you want? And then so which since we got N1 to N3, so again you can, because N3 will be the same, right? Because this is a condenser, 100% methanol condensed. So this will be N3, you got N3 here, N4. Okay, so you already solved these 4 unknowns. And what's next? So if I were you, the things change is this one, right? This, and then you will think, well, this might be a good idea. Condenser might be a good idea to do the thing, to do the mass balance. Okay, the balance on a condenser, because condenser is a molecular species. There's no chemical reaction, so you can do this as you learn before midterm exam, right? So easy. So please do this. So you can achieve N5, X5C, and X5H. Can you do that for me? Yes, you can, right? Yes, you can. Very easy. Okay, so you can achieve N5, X5C, and X5H. So let's mark the H5, N5, X5C, and X5H as from red color to blue color. Okay, so X5C and X5H will be the same as this one, right? Because this is a splitting point. So the fraction will be the same. So you mark this X5C and X5C and X5H. Okay, so what's the next? Next one, you might think, wow, Professor, can we do this? Yes, you can, but you'll realize this is related to N5. So there's no another specification. There's only one equations. This is not independent, 2 independent equations. So you have to go back to this one. So once you do the balance on a condenser, you solve the problem, you got some answers. And after that, you move back to this. You move back to the splitting point, molecular balances. And ratio species is the same, so it's not independent. So forget about this point and move to this one. Move to the mixing point. Okay? So let's revise this again. Once we get the mass balance for the reactor, we get N1 to N4, right? We got N1 to N4. And because this condenser, so since condensed will be the 100%, so N3 will be the same, N4 will be the same here. And then after that, we do the condenser, we got an answer of N5, XC5, F5C, H5H. And because this is splitting point, the fraction will be the same, right? For the purging stream and recycle stream. So X5C and X5H will be the same according to this stream. And this one is not independent. N sub R and N sub P is not independent. So let's move to the mixing point. So mixing point, how many input? 2 input, 1 output, right? How many unknowns here? 1, 2, 3. There are 3 unknowns. So 3 unknowns easy, right? So you can get 3 unknowns, 3 molecular species balance, carbon dioxide, hydrogen, and inner gas. Bingo, you can solve this problem. NR, N0, and XOC. Okay, so with this way of doing the job, I hope I work through this with you, and I hope you understand. And in your final exam, you can do this calculation easier. Okay? Right. And then back to the splitting point, you finally you get this number. So now is the way of doing calculation, and I think please read this by yourself. You can practice this. Okay? And you can get the answers. Right. So the final part is called flow chart scaling. You know, as I just told you that we forget about 155 first, and we had a basis in this stream. So once we get N3, there's a ratio of N3 to the 155. So you can scale up or scale down. That's what we learned before midterm exam, right? So if you know the ratio, you can change. If this ratio is about 10 times, so it's just times 10 for N4, N1, N3, and then N5 here. Of course, you don't change the ratio here, okay? You just scale up or scale down. So basis is 100 kilomoles combined, okay? So, and we got N3 is what? N3 is 14 kilomole. And then the text tells us that N3 is 155. So you just what? You just have 155 divided by what? Divided by 14. That will be 11.1. So that means you have to times all the numbers to 11.1 from the original number. Okay? Okay, and you got all the answers. So in the page 142, that's scaling table. I'm sure that please you can have a calculator. You can do it quick. Right. Okay. So key points for the example 4.7-3. That's why you need to remember. First, choose a basis. Forget about 155. And splitting point is the same molar ratio. You need to remember this, otherwise you cannot get the answer. And also condenser, remember the condenser. Right, okay, so this is going to the end. So this is one of very important example in the industry. You know, the methanol, Jiawan, is in a gas form. It's very expensive to ship. You know, you don't want to ship the gas from the Middle East to Taiwan. It's very expensive. Okay, it's same as you don't want to ship water. It's very expensive. You can have water in Taiwan. Why you need to have water, ship water from United States to Taiwan? And also methanol is gas. So normally you don't want to ship gas because the density is too low. You want to ship very high density. So gas is expensive to ship. It's usually converted into a carbon monoxide and hydrogen and then liquefy. So you change the methanol to carbon monoxide and hydrogen and then make it become liquefied. Okay, and what kind of chemical we want to have? Benzene. So a promising alternative is conversion to benzene to hydrogen and with the catalyst. Catalyst is kind of chemical which doesn't involve in a chemical reaction, but it helps chemical reaction. It helps the chemical reaction. Okay, it reduces the activation energy, so it can make the chemical reaction happen. Okay, easier. So methanol, this is called methanol dehydrogen atomization. We use MDA for short. So basically, you can regard something like this. MDA is like this. This is gas. This is liquid. So you want to ship a very valuable chemicals in liquid form, and then you ship to Taiwan and you convert it back. You just change it. Okay, this is kind of a process. So MDA is a key technology for exploration of the starting natural gas reserved by the direction conversion into the transportable liquid. So this is the process. Okay, so where is the purging stream? Here, right? And this can be regarded as a what? Recycle stream, right? Recycle stream is here. So again, you have a reactor, you have a separator, and here you just have one more is a methonator. Okay, that's it. And chemical engineers need to involve in this kind of process because you want to make money. You want to ship something more efficient. Okay. And this is a paper from Science, okay, in 2016. You know, if you can publish a paper in Nature and Science, you are famous. Okay. Very important journal. Right. So we finished this chapter. We finished this section, and 4.8 is kind we call combustion reaction. Combustion reaction. You already learned combustion reaction in the previous section, because it just involves oxygen, right? So the combustion reaction is what? It's a rapid reactions with a field. The fuel, it can be a liquid, right? It can be gas, it can be solid, okay? It's perhaps important, more important than any other classes of industry chemical reactions. It's very, very important for the combustion. You use combustion every day. Despite the fact that the combustion products, carbon dioxide, carbon monoxide, water, and sulfur dioxide are worth much less than the fuels burned to obtain them. Because, have a gas. If you use combustion process, the product is like this, which is not good at all. Then why you need this kind of reaction? What you need is energy, right? Tremendous energy. So once you do the combustion, you got energy, which is thermal energy, right? Thermal energy. So the significance of these reactions lies in the tremendous quantities of the energy they released. Okay, the energy that used to boil water to produce steam, which is then used to drive the turbines that generate most of the world's electrical power. So when you see an airplane has an engine, right? Engine use fuel. Fuel have chemical reaction with oxygen and become energy. So energy drive the turbine go, right? Drive the turbine and let the airplane go. Okay, fly. And this is what very important. We call thermal power station. So what's a thermal power station? You have fuel, which is coal. It can be gas, right? It can be methane gas. It can be liquefied gas, 天然气, right? 液化瓦斯. It can be coal, 煤. So you put this and you burn this and you generate what? You burn this and then generate what? Energy. So, and the energy give water temperature, increase the temperature of water. So water become what? Steam. And steam has a very high energy, and steam drive the turbine to what? To rotate, right? To rotate. And then once steam drive the turbine to rotate, and you have a generator, electrical generator, and the turbine rotate and make the electrical generator, and we get the electricity. So that's what we use every day, right? So this important thing is what? The chemical energy convert to the thermal energy. The thermal energy convert to the mechanical energy. Mechanical energy, or we can call it kinetic energy. Mechanical energy convert to what? Electricity. And we use electricity. Okay, so all the conversion has a conversion rate. So if we increase the conversion rate 1%, 2%, you become very rich. That's what everybody want to think. You want to increase, you save energy. You got Nobel Prize. Okay, if you know how to save energy, how to increase the efficiency of from chemical reaction to thermal energy, from thermal energy to mechanical energy, from mechanical energy to electrical energy, and that's all way through. Okay, so who need to work in this kind of project? Chemical engineers and also mechanical engineers. So in a thermal power station, fuel such as coal, oil, or gas is burned in a furnace to produce heat, right? So the heat is used to change water to become steam, okay, in the boiler. So steam drives the turbine from heat to kinetic energy. So this drives the generator to produce electricity, kinetic to the electrical energy. So basically, again, I want to remind you that this is a kind of very important process. Chemical energy, thermal energy, convert to kinetic energy, and then electrical energy. Okay? Right. This is one of the largest fire power station in United States, okay, in Georgia. Okay, so this is a power plant. Right. So the job of the design power generation equipment usually fall into mechanical engineers. So how to design this is the job for the mechanical engineers. But what happened to the chemical engineering? Okay, but analysis of the combustion reaction and the reactors and the abatement and control the environment pollutions cause the combustion products like carbon dioxide, carbon monoxide, sulfur oxide is a problem with which chemical engineers are heavily involved. So chemical engineer is kind of a process engineer. You need to go through all the process and try to reduce the trouble and try to increase the efficiency. Okay? Right. I will skip this section because for the mass balance, this concept will be all the same. Okay? So the important thing I just want to tell you is that I just told you from the page 1 to page 7. So I will skip this. This section. So please read this by yourself. And this is one of the important things. It's called stirring engine. This is we call 外燃机. You heard about 内燃机, right? This is in the very beginning. 外燃机. This is from thermal chemical energy transfer to thermal energy. Thermal energy change to what? Mechanical energy, which is kind of it will move. So this is kind of stirring engine, and very important energy, right? You can make this to let the car move. Okay, right. That's it. So that's it for the chapter 4. So I want to talk a little bit about the chapter 5 today. Okay, we finished the most important chapter, which is chapter 4. So if you know how to do the mass balances using the concept I just told you, and that will be you can apply the same concept to the energy balance and also momentum balance, for example, something like this. No, forget about momentum balance. You can use the same concept to the energy balance, which is in the chapter 7. Okay, but and what happened to the chapter 5 and chapter 6? That's something to do with chemical engineering. We want to talk about liquid, gas. We don't talk about solid that much, and then we want to talk about specification. As a knowledge for the chemical engineers, you need to have some kind of basic knowledge like vapor pressure. Excuse me, like vapor pressure. What's the vapor pressure of the water at 25 Celsius, and how to get it, and this kind of specification. Okay. So, and you need to know the balances between liquid and solid. Liquid and gas. So there are two phases. There's a situation which is two phases, and you need to know the concentration of the methanol in the gas phase and how to do the calculation. And this is kind of specification. Okay, and this is important for you to know. That's why we introduce you when you are in the first year, and we'll move to a more difficult part concept in the second year and third year in your program. Okay, so now let's talk about, this is very easy part. So let's start to know, we start from the single phase first, and then chapter 6 we'll talk about two phases, liquid and gas. So let's think of the single phase system first. So in chapter 4, we know that information is given in a problem statement. I give you what's the vapor pressure, I give you the concentration, okay? But here I don't. In chapter 5, is to determine various physical properties and use them to drive additional relations before the material balances. That means that you need to know some of the basic knowledge about the specification, and then you can solve the problem using mass balances. Okay, so this is what we start to work with, right? You have the specification and determine the variables. So variables such as what? Density. Okay, what's the density of the gas in what pressure or in what temperature? Okay, and then what's the vapor pressure? And what is the solubility? Okay, solubility, you know the solubility of oxygen in water. What's the solubility? Okay, you also need to know this. And the heat capacities, this will be in chapter 7. And how to determine them, how to make this, how to determine. Right, how to determine vapor pressure, for example. First of all, check. As a chemical engineer, the important thing is to check the number, find the books, and get the answer. That was me when I was a student. I need to find books. I need to go to the library. And now you don't. You just Google it, right? Google it. But you might get many different answers. And according to your professional judgment, you need to know which one is the best, which one is the right answer, right? So one of the very important handbook is this Paris Chemical Engineers Handbook. This was like a Bible for me when I was a student. You have everything in it. You have everything in the book. Again, I want to tell you now you go to internet, you Google it, you can find the answer. Okay, and the other one is chemical abstracts. We use CA. The second method is estimate it. How to just simple know that how to estimate. So if you have a single pure component substance, that will be easier. That will be easy. But if you have a mixture, then that won't be so easy. Then what happened? You might be able to find a chart Okay, you might be able to find a relationship between the gas and liquid. The third one is what? Third one is measure it. You just do the experiment and find out, right? So if there is no literature available, and then you just do the experiment. So this chapter, easy. We just want to tell you how to determine the density of gas and liquid. Okay, we don't talk about solid because that's called material science. I will talk about this when you are in second year. So how to determine the density of gas and liquid of the mixture. Okay, so we use M is a mass, N is a mole, right? Okay, or over that. So section 5.1 is density of solid and liquid. And section 5.2 is the density of the ideal gas. And of course, section 5.3 will be a density of non-ideal gas. Right, so the liquid and the solid density, I'm sure you know that, density related to the temperature. Is it density a function of temperature and pressure? Yes, it is, right? It depends. It depends on, you are talking about solid, liquid, or gas. So the density versus temperature is what? If temperature increase, volume increase. The volume increase, what happened? The density decreased, right? So temperature increase, density will decrease. You can think of solid. You can think of the case of water. If we increase the temperature from zero, that will be from below zero, that will be ice, right? Ice. And then if we increase the temperature above zero, that will become water, right? From ice become water. So density of water will be lower. Okay. Well, no. Let's don't use water as an example because water has hydrogen bond, so density will be little bit different. Let's use carbon dioxide. Okay, dry ice. Have you heard about dry ice? Okay, if temperature below a certain point, carbon dioxide will be dry ice. The density will be very high. But if you increase the temperature, and that will become carbon dioxide liquid. Okay, which is very small gap. And then density will increase. And then what happened? If you increase the temperature, carbon dioxide will become gas. The density will become very low. Okay? How about pressure? The change in the pressure does not cause significant change in liquid and solid densities. These substances are therefore called incompressible. Okay? So pressure normally doesn't affect the density that much, but it does a little bit. Okay, how to find out the density of liquid and solid? Easy. Again, 3 methods. First, look it up. You find the books, right? Different temperatures. Okay, if you want to find some substance, you can get the textbook, the table B1, and in appendix B, you can get it. Again, I just told you that the Paris Chemical Engineers Handbook, you can get an answer. Or what you measure, right? You measure the density. Okay, so estimate it. If non-data available, a mixture of liquid. For example, a mixture of liquid, you cannot find it from the textbook because there are so many kind of combination. So that means you need to start to work on how to estimate the mixture, the density of the mixture substance. So there are 2 methods. One is by we call volume additivity. Okay, we call 体积加成. So if you want to assume if we have only 2 substances, the volume is value is called V1 and V2. And we understand the V1 has a low 1 and the V2 has a low 2. And X1 and X2 is the fraction of these materials in this mixture. So you have M here. So M is total mass. So as you put these two together, if the value can be combined together without any problem, so V1 plus V2 will become this. And as you know, as you do something like this, you move M here. So you understand the one like reciprocal, a reciprocal of the density. This is called what we call reciprocal. All right, reciprocal of the density will equal to what? X1 divided by low 1 plus X2 divided by low 2. So this is what we call volume additivity. Okay, but if you have 3 substances, 4 substances, 5 substances, you put it together and you make it as kind of summation, right? The reciprocal of the average density will become the summation of the xi divided by low I. X is what? X is max fraction, low is the density of the species I. You don't need to remember this equation because this is easy, right? This is easy. This is what we call volume additivity. This is equation 1, equation 5.1-1. And the other one is what? For the pure component xi, you can have a fraction of the density using mass fraction. Instead of value additivity, you use mass fraction, which is easier. You have learned this before. Low over bar means what? Average, the average density of the mixture is the summation of xi times low I. Xi is it's molar fraction. Okay, this is equation 5.1-2. So which one is better? Which one you need to use? Equation 1 or equation 2? So find out the density of liquid and solid. There's no correct answer. Sometimes some species is suitable for use equation 2. Some mixture is suitable to use equation 1. So one of these estimation formulas might work better for some species, and the other might work better for other species. Okay, but there's some general rules. This is one example. If we have mixture of the H2SO4 and a mixture of H2SO4 with water, use equation 2 will be better. If you have a methanol, CH3OH together with water, equation 1 will be better. Okay, so there's no right answer. So this is one of the examples showing you that value additivity normally is used for the liquid species with the similar molecular structure. If you have a similar molecular structure, and then they suggest these textbooks suggest us to use value additivity. For example, all straight chain hydrocarbon, excuse me, like this, N-pentane, hexane, and heptane. You can use this for the mixture to understand the density. You can use this value additivity. For the fraction of density, there's no general rule. Okay, so this is the example, the determinant of the solution density. Quick. So for the you have 50 weight percent H2SO4 and 50 weight percent H2O at 20 Celsius, and you want to know what's the density of this mixture. And you can use 2 methods, right? You can check. First of all, you check the book from Paris Chemical Engineering Handbook. This is correct answer because the Bible always tell you the truth, right? So this you have 1.3951 grams per cubic meter. Okay, this is answer. But however, if you use two equations to solve this to get an answer, for example, for the value activity, you get this, you get the density will be 1.29 grams per cubic meter. Okay, but for the average density, you put the equation in here, then you got 1.42 grams per cubic meter. So which one is close to the true the volume of the measurement from the textbook? This is value activity, though is 1.29, and this average density, which is 1.42. Obviously, this one is better, right? This one is better. But anyway, there's no exact rules, but just give you an example. Right. So since we run out of our time today, and I think on Wednesday we are going to talk about ideal gases.